Welcome back. Hopefully you've taken this pop quiz online on Canvas. And if you haven't yet, then please stop the video now, go back and take your best guess at which is the correct answer. Okay, so I'm going to reveal the correct answer here and talk about why the other ones are not correct. So here's the correct answer. But first I'd like to address each of these other points here. So the reason why this point is not true is that spontaneous processes do not always release heat. For instance, vaporization actually does not release heat, it absorbs heat, but it will occur at high enough temperatures spontaneously. That's because the spontaneity is determined by delta G, but the amount of heat release is due to delta H. And delta G is partially dependent on delta H, but also delta S and temperature. Okay, number two, the products of the reaction are naturally occurring substances. That's a pretty irrelevant point with regards to how much heat is released. Number three is the correct one. Stronger bonds are formed in the products than those broken in the reactants. Now remember, stronger bonds implies a lower energy. So there would be a lower bond potential energy. Therefore, there's going to be a lower enthalpy, and therefore our delta H is going to be more negative, and therefore our Q is going to be more negative. So it's going to be releasing a lot of heat. Number four, there are fewer moles of gas molecules in the products than reactants. That's something that might affect the volume of the system, but that wouldn't really affect the heat of the system. Okay, next I want to talk about the Clausius-Clapeyron equation. Now remember, the Clapeyron equation that we had in the last video was the slope of the pressure with respect to temperature on a PT phase diagram is delta Sm divided by delta Vm of the coexistence curve. And you might ask, well, is it the delta S of going from which phase to which other phase? And the answer is it doesn't really matter, because as long as we're consistent about the phase transition between the entropy and the molar volume, then we're going to get the same result, because we're dividing a negative number by a negative number or a positive number by a positive number. Incidentally, this also happens to equal the extensive quantities as well as the intensive quantities. Okay, so the Clausius-Clapeyron equation applies to situations where we have a liquid-gas coexistence, because the Clausius-Clapeyron equation is going to give us the vapor pressure, as it says right up there, and the vapor pressure is in the case of a liquid-gas coexistence. Potentially also a solid-gas coexistence, but mainly we're considering liquid-gas. So that means that the chemical potential of the gas is equal to the chemical potential of the liquid if the two are coexisting. Remember, because those curves are overlapping each other. Okay, so that implies that the delta Gm of the gas is equal to the delta Gm of the liquid. So this is similar to what we saw with the Clapeyron equation. Now I'm going to indicate here a Gibbs free energy of the vaporization. So that is specifically the Gibbs free energy for the transition from the liquid state to the gas state. And since the two are just equal to each other, that's going to equal 0. We can also write that the Gibbs free energy of the vaporization, that's just this one here, and I've just shortened it down to vape for vaporization. It's going to equal the enthalpy of that vaporization minus T delta S vaporization. But of course that just equals 0. So that means we can set those two equal to each other. Then dividing both sides by T, we get what the entropy of the vaporization is. Delta Hm vaporization divided by T. This should look familiar to you. We did something very similar in previous chapters, chapter 5 specifically for phase transitions. Okay, so now we're going to make an assumption, a key assumption, in order to get to the Clausius-Clapeyron equation. There's going to be a certain change in the molar volume of the vaporization, and that's going to be the final state molar volume, so that's the gas, subtracted by the initial state, which is going to be the molar volume of the liquid. But we can assume that this is going to be approximately equal to just the volume of the gas, because the gas tends to occupy so much more molar volume than the liquid does. So here's one of our key assumptions. So now we can plug both of these quantities into the Clapeyron equation. So let's do that now. The slope of pressure with respect to temperature, remember, was delta Sm divided by delta Vm, and we're talking about the liquid-gas coexistence curve. So this becomes delta Hm of the vaporization divided by T Vm gas. All right. Now, for the volume of a gas, we're going to make another key assumption, which I'm indicating with a star, that we can just use the ideal gas law. And the molar volume is just volume divided by number of moles, which is just RT divided by P. And I can plug that in right there. Then what I get is that the slope of pressure with respect to temperature is just enthalpy of vaporization times the pressure divided by RT squared. Okay, so this is actually a differential equation, and differential equations tend to be very hard to solve. They're sort of the subject of math that comes after calculus. But I'm going to show you how to solve this differential equation because this type appears quite often in science, and it's relatively simple to solve. And the way that we do it is we have to get all the variables of the same type over to the same side. So I'm going to multiply both sides by 1 over p and both sides by 1 over dt. And I get 1 over p dp delta Hm vape over r 1 over t squared dt. Now I can integrate both sides, and this is going to be from one pressure to another pressure because this is a pressure integral, but then over here it's going to be one temperature to another temperature. If you want to attempt to integrate this yourself, feel free to pause the video right now and give it a try, but I'm just going to tell you the answer right now. The log of P2 over P1 negative enthalpy molar vaporization divided by R 1 over T2 minus 1 over T1. There we go. That is the Clausius-Clapeyron equation. I almost forgot to mention one last key assumption. So here's another star to represent another key assumption, that delta Hm of vaporization is constant with respect to changes in temperature. And this is typically a valid assumption that we can make. Okay, a couple of final points before we get to the next clicker quiz. It's worth noting that the enthalpy of sublimation is equal to the enthalpy of fusion, which, by the way, is the transition from the solid to the liquid state, plus the enthalpy of vaporization, which is the transition from the liquid to the gas state. Sublimation is the transition straight from the solid to the gas state. This equation is only exactly true at triple point. Okay? Otherwise, we have to account for the, albeit small, enthalpy change as we increase the temperature or pressure, especially pressure. A couple of more terms to just know. The normal boiling temperature is the temperature where water boils at 1 atmosphere, but the standard boiling temperature is where water boils at 1 bar. So that's a tricky and slightly annoying distinction, but make sure that you understand the difference between those two. And then the book also mentions Troughton's rule, which is the assumption that the entropy change of vaporization is going to be approximately 90 joules per Kelvin mole. And that's typically only valid for fairly non-polar liquids that don't have strong intermolecular interactions.